Greetings, chemists. This lecture is going to be about classic atomic structure experiments. Things that led to the discovery of different parts of the atom. And we're going to focus on two in particular. First, at the beginning of last century, there were a couple of chemists, one named Ramsay and one named Rutherford, that were studying this isotope called uranium. And they noticed that if you took like a block of uranium and you put your hand close to it, you felt hot. You could feel heat coming off of it. It felt like it was radiating heat. And I thought, well, what's going on? And so they studied this. And this guy Ramsay looked at this, it was a metal essentially, and it found that it was giving off a gas. And they caught the gas and they looked at it, at its spectrum and everything, and they identified that it didn't look like any of the gases on Earth that they had identified up until that point. But it looked an awful lot like some of the gases they were seeing, or one of the gases in particular that they saw in the sun. And so they named it after the god of the sun. If you're into Greek mythology, they used to name the god of the sun Helios. And so this gas that was kind of coming off of the uranium atom, they called it helium. And they figured it's another atom. This uranium is made up of little atoms of uranium, and they guessed that what must be happening is those atoms are splitting apart into smaller atoms, and one of the atoms that comes away is this helium. And it turns out it was leaving behind other discolorations, and they found that those other discolorations were like, I think, thorium. And so it looked as if a uranium atom could split into pieces, and those pieces themselves were other atoms. So that was Ramsay. This guy Rutherford says, well, let's explore that further. I'm curious about these helium particles, right? It's shooting off atoms. I'm going to try this. And he has his students set up a uranium block like this. So we have some uranium, call it U for uranium. And he put it inside a block of lead, a big, heavy block of lead. Now, that block of lead is so thick and dense that it caught all the radiation that went like this, right, into the edges and soaked it up. But there was a channel out here where it could send those uranium particle, or those alpha particles, they call them alpha particles, those helium particles out this way. So he set it up where it's like a gun, right? It can shoot these little pieces of itself, these little helium atoms out this way. And he took a foil, like, you know how you have aluminum foil at home. He made a foil, but he made it, instead of out of aluminum, he made it out of gold. Gold is this very dense material. And he wanted to see what would happen when he shot this uranium, these alpha particles at this very thin gold foil, because there was a chemist at the time, got all these chemists' names, so Rutherford is running this experiment. It's famous as Rutherford's gold foil experiment. There was another chemist at the time, J.J. Thomson, we'll talk about him in a little bit, who thought, well, matter is basically like one big block with a little bit of positive charge, a little bit of negative charge, and when you shoot these heliums at it, it's going to go through. It might deflect a little bit, and when it gets knocked off course by these positive and negative charges, we'll get to see like a charge density ratio. We're kind of looking for that. And Rutherford says, cool, we'll try this. So what he does is he sets up detector screens. All the way around the foil. And his thought is, what happens is, if any of these helium atoms make it through and to the other side, wherever they hit, there'll be a big bright spot. So if it like bounced off this way, we would see it on the screen. We would know where these things are hitting and where they're being deflected. Okay? what does he see? Well, here's the result of his experiment. He sets this up, he lets it go for a long time, and these helium atoms are going through, they're hitting the gold foil, and almost all of them, bright spots right here, just behind, like they went straight through. With occasionally a bigger deflection. You do see some over here, you see some over here, you see some spots over here, but most of them, like 90-something% of them are here, a little bit here. But occasionally, you get a spot back here. And Rutherford was stunned. His words, he said, it felt like I shot a bullet at a tissue paper and it bounced. Because this foil was very thin. He said, how are we bouncing atoms off of that foil if, like Thomson says, if this is just a nice, even, universally distributed piece of matter, they should just shoot right on through. But they didn't. They bounced. He said, well, here's my thought. 90+% of these atoms go right through the foil, no problem. But maybe like 1% or even less than 1% bounce. That must mean that inside of this foil, there's a lot of just low density area or no density area, and there's a little tiny, like right here maybe, and maybe right here or right here is like a really high density spot, something so dense that a helium atom could bounce off of it. And so he came up with the idea that matter has little nuclei and lots of empty space, and then another little nucleus over here, and lots of empty space in between. And so when he shot these particles, most of them are going right through. And then only occasionally do we get a bounce. Or if you hit, a little further up, make it a deflection this way or something. That's where we get this idea. And you've probably seen this drawing of the atom, which is that you have a little nucleus in the middle, a bunch of little particles, then you have this like electron cloud outside, but there's a lot of space in between. How much space, you might ask? To put it in perspective, if this nucleus was the size of a marble, the empty space around it where the electrons are, we call that the electron cloud, would be the size of a football field. A marble in a football field. That's the ratio of space to density in an atom. Which is a big deal. Okay, so let's go back to Thomson. Why did Thomson think of a different model? Thomson thought of it this way. What Thomson was doing is he took a disc, a metal disc, and he put it attached to an electrode. Kind of like a battery. Something with a potential difference, something with a positive end and a negative end. And he had a detector screen over here. And he put it in a big tube and sucked all the air out of it. And he found that what happened was if you got enough electric potential with this vacuum tube, a stream of particles would travel from one side to the other. You could get a flow of particles. Now he came in with a magnet. Actually, it wouldn't have been a horseshoe magnet, it would have just been a bar magnet. So here's a magnet, let's say, with a north pole and a south pole. Probably going to get that wrong. And he found that when he put the magnet near the stream of electric particles, he got them to move. He got them to deflect sideways. Well, a particle will deflect in a magnetic field only if it has a charge. He was able to determine the charge on these particles was negative. So he said, look at this disk. Now this disk itself was not charged. Not before he attached it to the battery anyway. So this disk was neutral. Actually, even after connected to the battery, it'd still be neutral. A neutral disk that is able to give up negative particles must also have positive particles, right? In order to be neutral, you have to have as many negatives as you have positives. So Thomson said, well, those little negative pieces, those are the parts that I'm being able to shoot off the disk with my electric potential. This was called a cathode ray tube. In my cathode ray tube, I'm able to shoot off these negative particles. So this must be what matter looks like. He called it the raisin pudding model. If you're not familiar with British cooking, that just means like a big piece of bread with some raisins in it. He said, we've got the raisins are like the negative charges, the bread is like the positive stuff. We've got to have both kinds of charges in there for everything to be neutral, but they have to exist there and they have to be able to move off because I'm able to shoot them across this little gap so they're not blocked in place, let's say. He was only able to get the negative charges to move. So he called those negative charges electrons, and that's where we get the idea of an electron. Now, in his model, he didn't know any better. He says that's all uniform density. And it wasn't until Rutherford came along and shot particles at it and said there can't be uniform density. There have to be little, small, super dense spots and a lot of empty space. Okay? Otherwise, I wouldn't be able to bounce bullets off of it. Bullets, in this case, is pieces of uranium or helium atoms. Okay? So these were the two of the big classic experiments that kind of lead to our current model of the atom, which is a bunch of little positive charges. In fact, we think the nucleus, if we look deep at the nucleus, we now have this idea that the positive charges are in the nucleus. And the electrons are the stuff on the outside, and that's why they're easy to move around, where the nucleus is hard to get to. And later on, Chadwick comes along and discovers neutrons and says, hey, there's more mass in there than there are positive charges, which is fine. So this is our thought on the atom. Very tiny nucleus filled with high density, lots of mass. In fact, all the mass of the atom, more or less, more than 90% of the mass of the atom is in the nucleus. And then little, not dense negative charges that are on the outside in some cloud, which we'll talk later about how they're organized. Okay.